Okay. So if we're just going to go to a logarithmic form given an exponential form, we have to understand a logarithm equals an exponent. And with the logarithm, every logarithm is going to have some base. So the base on this logarithm is going to be the base in the exponential piece up here. So here, that base is going to be 2 on the logarithm. If every logarithm equals an exponent, then I know this logarithm I'm trying to set up is going to equal the exponent up here, 4. But the logarithm's a function, and I need something to plug into that function to get this value of 4 back. So that's where you take this 16 that's left over and you plug it in. So I go from exponential form to logarithmic form here. I get log base 2 of 16 equals 4. That's it. So similar example over here. We got 4 to the negative second equals 1 over 16. So recognize with all these equations we're giving you, they're true statements, right? So the logarithmic equations we're getting back here, the logarithmic form we get back here, that's going to be a true statement as well. To write this one out, start with the log idea. The base on this logarithm is going to be the same as the base in the exponential piece up here, which is 4. Okay, you saw how the previous one unfolded. So we know we're going to take 1/16 here and plug into this logarithm, because overall this has to equal the exponent, and the exponent was negative 2. So log base 4 of 1/16 would equal negative 2. All right, last one down here, you got 10 to the negative first equals 0.1, so it equals 1/10. That should make sense. Here I would have log base 10, since that's the base on the exponential piece. 0.1 would be plugged into that logarithmic function, and that would equal negative 1, because negative 1 was the exponent on the exponential piece. All right, on this next part, we're basically going to go the other direction. We're going to go from the logarithmic form that's given over to the exponential side. So if you think about what we just did, now just go in reverse. We want to start, since we're building something exponential, with the base value here on the logarithm. We want to start with that 10. A logarithm equals an exponent. So here the logarithm equals 3. That 3 is going to be the exponent on that 10. In the end, that's going to equal the value we plugged in the logarithm, 1,000. So the equation we get back should make sense. This other one, kind of sliding off the screen here. We've got log base 8 of 4 equal to 2/3. So if I want to write that in exponential form, base would be 8. Logarithm equals an exponent, so here the logarithm equals 2/3. Exponent would be 2/3. This is all going to equal what we're plugging in the logarithm, which is 4. Now what's nice about logarithmic form and going over to exponential form, and this can prove useful as you go along here trying to calculate some of these logarithms out. I call this kind of the merry-go-round effect. Notice how you set this stuff up. You always start at the base. So I start here with 10. I'm raising it to this guy over here. And then that's equaling that part right there. Kind of creates a little circle effect. Same with this one. Start with the 8. Raise it to the 2/3. Let that equal that part there. Works every time. Move on. Okay, here we're going to do some evaluating. If you're really comfortable with exponents, exponent rules, you can start cranking these out pretty fast. But how I'm going to introduce this to you, I'm going to introduce this to you as if we're solving an equation. Okay? As you start to pick up on the pattern, you may not need this procedure anymore. But let's say on this first one I've got log base 64 of 4. I want to know what that equals. Since I don't know what that equals, let me use a variable. Let me use an x. So now I've created an equation where I've got to solve for x. Well, I think more clearly as far as solving is concerned in terms of exponents. So let's take the logarithmic form and let's convert over to the exponential form. Let's ride the merry-go-round. Let's take 64 here, raise it to that x, let it equal 4. So 64 to the x equals 4. So as we played with the equations before, we found that creating common bases, prime bases, that was useful, right? Here we could do prime bases, but 64 you could also just choose 4 as a base, couldn't you? Because 64 is 4 to what power? It's 4 to the power of 3, right? 4 to the third is 64. So if you have 64 to the x, you got 4 to the third raised to the x. That equals 4 over here. Now, power on this 4 obviously is 1. If we do power to power over here, well, we'd be multiplying. You'd have a 3x there. And with these bases being the same, these exponents would have to be the same, so 3x would have to equal 1. I'm trying to figure out what x is, so x must be 1/3. See, that way always works. But as I said at the beginning, if you're comfortable with your exponent rules and properties, you may recognize that, okay, 64, how does this compare to 4 right here? Well, if I took the cube root of 64, that would give me 4, right? And how do you represent a cube root as an exponent? You use 1/3. So right away, you could have said, hey, that's 1/3. That would work. Okay, next one here. You got log base 1/4 of 16. Just to be consistent with how I presented the last one. Let's let that equal x. Let's set up the exponential form. So it'd be 1/4 to the x equal to 16. We're trying to create some common bases here. Looks like some 4s might be in play. Not really liking the fraction here, but I do understand that if I want to use a reciprocal here, I could. Reciprocal of 1/4 is 4, but I can only use that reciprocal if I make this x here negative, right? Got to incorporate some negative exponents to use those reciprocals. Now that equals over here 16. If the base is 4, 16 would be 4 to the second. So now you got your common bases. You set your exponents equal to one another. You got negative x equals 2. So if negative x equals 2 and you're solving for x, x is just negative 2. Another one sliding off the screen over here, but over here we've got log base 36 of 1/6. So if I let that equal x, we've got 36 to the x equal to 1/6. So 36 to the x equals 1/6. Start thinking common bases here. 6 would probably make sense. 36 we know is 6 to the second. So it'd be 6 to the second raised the x. That'd be 6 to the 2x equal to. Got that fraction, not really digging that fraction, so let's use some reciprocals here. Instead of 1/6, we'll say 6, but what's the power going to be on that 6? Negative 1, because you're using reciprocals, so introduce the negative exponent. Bases are the same, so exponents have to be the same. 2x equals negative 1, meaning x equals negative 1/2. Just to run through a few of them. I'm going to go back to some of those properties that we listed. You've got to recognize that you've got some exponential ideas plugged into logarithms, or vice versa, you got logarithm ideas plugged into exponents. If you go back to that list of properties, we could, on this first one, let it equal x and do our little merry-go-round. That would definitely make sense here to get that answer, but recognize since this base is the same as this base, then all my answer is going to be is the exponent, 10. Now, working my way across here, I've got log base 3 of 9 to the 7th. Again, I could let it equal x, ride the merry-go-round. But this 3, I know I could take this 9 here and convert to a 3 base pretty quick, right? That'd be 3 to the 2nd. So if this is just going to be 3 to the 2nd, I'm raising that to the 7th. This is the same thing as 3 to the 14th, right? So my answer here is just going to be 14 now that I've created the same basis. The one in the middle is a little different because now you've got the logarithm floating around up here as an exponent, but it's still based on that whole inverse idea. Because the logarithm up here in the exponent has the same base as the base down here for the exponential expression overall, it's kind of like these ideas are canceling themselves out, leaving you with just 45. So if I've got a logarithm base 1,000, you've got 10 to the 12th plugged in there. Now let's think about this. 1,000. 1,000 is 10 to the 3rd power, right? So if that's 10 to the 3rd power, is there a 10 to the 3rd power in here? There is, if you do this, 10 to the 3rd raised to the 4th, right? 3 times 4 gives you 12. So really, what I have there is the same. So now I've got the same bases. You've got 1,000 here, you've got 1,000 here. What's my answer going to be? Well, my answer is going to be that leftover exponent of 4. All right, this last one. This last one's kind of tricky. Might be a little tricky to see how it works, but you've got a square root of 6 here as your base. It'd be real nice just to have a way to relate to a square root of 6 here. Well, since I'm dealing with kind of a base 6 idea, maybe I should look at this 36 as 6 to the 2nd. As long as I'm looking at exponents, because I know that's how I'm going to get to my answer, maybe I should look at this square root of 6 as 6 to the 1/2. You multiply that together, you've got to add those exponents, right? So if I multiply that together, I've got 6 to the 2 1/2, which is 6 to the 5/2. So right here, base is square root of 6, which is 6 to the 1/2, right? And here I've got 6 to the 5/2. Anybody know what the answer is? What if I took this 6 to the 5/2 and wrote it as 6 to the 1/2 raised to the 5th? Right? There's that square root of 6, right? So here's your square root of 6, here's your square root of 6. Those ideas essentially canceling themselves out, so 5 would be left as your answer. Now that we've done enough of these, if we take the x approach out, maybe just use some properties, maybe just use the understanding that a logarithm equals an exponent. You look at this first one where it's log base 2 is 64. That's basically saying, all right, 2 to what power gives me 64? What is it? It's like multiple choice. It's 6, right? Okay, let's go on the flip side down here before we work our way across. You've got log base 64 too. If I took a certain root of 64, I'd get 2 back, right? What would that root be? The 6th root. Right? If 2 to the 6 equals 64, take the 6th root of 64, you get 2 back. So as an exponent, we could represent that 6th root as 1/6. All right, this one over here, we've got a logarithm. Notice no base is written. So I was talking about this earlier. That base would be 10 when it's not written. And you've got the cube root of 10 here, which is really 10 to the 1/3. So what's that going to equal? Same base, right? That's just going to equal 1/3. All right, so we conclude with solving some equations. Now that we've seen how you can take a logarithm, set it equal to x, and then solve for x, these should be pretty straightforward. You know, if I've got log base x of 27 equals -3, to set this up in an exponential form, I'm going to take my x, raise it to the -3rd power, let that equal 27. Once again, depending on how comfortable you're getting with this concept at this point, you may already know what x is. But if we go through the process here and we solve, I'm going to use this trick. I know that x to the -3rd is 1 over x to the 3rd. I get that. But if you recall, because we've seen this now a couple of different times, I could change this to a positive power if I apply the reciprocal to the other side. One way or another, whether I change this to 1 over x to the 3rd or whether I do what I just did here, one way or another, you will get to this point in the process somewhere, okay? Now, trying to get rid of that 3, we can look at this 2 ways. We could look at it as I'm raising both sides to a 1/3 power, right? But if I'm raising both sides to 1/3 power, I'm basically taking the cube root of both sides. So in taking the cube root of x to the 3rd is x. Cube root of 1/27 is 1/3. So the base here, that x we're looking for, would be 1/3. All right, so log base 2 of x equals -4. This one's actually really nice to solve because once we take this 2, raise it to a power of -4, that's going to equal the x we're looking for. So 2 to the -4th equals x. To get rid of that negative exponent, we make this 1 over 2 to the 4th equal to x, meaning x must be 1/16. All right, last one. You've got log base 1/3 of x equal to -2. So 1/3 raised to the -2 power must equal x. We know to get rid of that negative exponent, we're just going to take the reciprocal here on that 1/3. So that's going to make that 3 to the 2nd equals x. So x is just going to be 9.